Hello students, earlier we discussed about the limit and continuity of the complex function, and using those concepts now we discuss the differentiability of a complex function. Now fz is a single valued function and defined in a domain D. Why it is necessary to define in a particular domain? Because function is a single valued and in a particular domain, if limit exists and unique, we know that there are some functions which are not continuous in that domain. For example, if we take a function fz equals to z over z minus 1. It is a rational function and we know that in the domain mod z less than or equal to 1, this function does not exist at z equals to 1. That's why this function is not continuous. जब function defined ही नहीं है, when function is not defined, then how we find out the limit and how we discuss the continuity of this function? It means domain is necessary for discuss the limit and continuity of the function. And function must be a single valued function in that domain. Then, if this limit fz plus dz minus fz over dz as dz tends to 0 exists and unique, then function is said to be differentiable, and this limit is written as f dash z, or this can be written in this way: f of z minus f of z0 over z minus z0 as limit z tends to z0. If this limit exists and unique, then this limit is written as f dash z0, and we say that function is differentiable at the point z0 or at 0. 0 means 0 plus iota 0. तो at 0, और इसको हम लिखते हैं at 0 और origin. Function is differentiable if limit as z tends to 0 f of z minus f0 over z exists and unique. In this way, define differentiability of the function at z0, at 0 or at any point of the domain D in which function is defined and single valued. Now, there is a necessary condition for a function to be differentiable is continuity. If function fz is defined and single valued in a domain D, then continuity is a necessary but not sufficient condition. मतलब function must be a continuous function, but it is not necessary that it is differentiable also. But if function is differentiable, then necessarily function is a continuous function. This can be easily proved. Limit of continuity of the function, as we discussed in the earlier lectures, as z tends to z0, if limit of the function is at z0, if function is single valued and defined in a domain D, then function is a continuous function. और अब हम इसको लिखें तो इसको हम लिख लेते हैं fz minus fz0 less than epsilon whenever 0 z minus z0 less than beta. This is the definition of the continuity. Now, continuity is a necessary condition to function be a differentiable function. Discuss difference fz minus fz0. Limit z tending to z0. Consider this. Limit fz minus fz0 over z minus z0 into z minus z0. मल्टीप्लाई भी कर दिया और डिवाइड भी कर दिया. Now this is f dash z. If this function is differentiable, then it is necessarily a continuous function. We are proving this part. Now this limit as function is differentiable, it means limit of this function is existing and it is unique. Then by this definition, we write it as f dash z0. It is limit as z tends to z0, z minus z0. But as z tends to 0, this is tending to 0. Therefore, it is 0 on the limit value, or this gives us limit of fz equals to f of z0 as z tends to z0. The function is a continuous function when function is a differentiable function, but converse is not necessarily true. It can be easily proved. The converse of this theorem is not necessarily true, can be proved by this example. If we take fz equals to mod of z square. Now this function is continuous, but it is not a differentiable function. This can be easily proved because mod of z, when z is x plus iota y, then mod of z is square root of x square plus y square, and mod of z square is x square plus y square. Here x is a real number and y is a real number. Therefore x square plus y square is a real number, a real function, and we know that this algebraic function is a continuous function. Therefore we can say that fz is continuous everywhere on the plane, but it is not necessarily a differentiable function. It is differentiable only at the origin. We are proving this fact. Now, to prove this, we have to find this limit for this function. Now, we can write limit del z tending to 0 mod z plus del z square minus mod of z square over del z. If this limit exists and it is unique, then this function is a differentiable function. We have proved here that function fz is continuous function. Now to prove it is not differentiable, we take a particular example. If we prove it for a particular example, then we can't say always if function is continuous, then it is necessarily a differentiable function. Now for this example, now limit del z tending to 0. This can be written as, we know that mod of z square is z bar. Using this result, we write it as del z plus del z, z bar plus del z bar minus z bar over del z. Or this can be written as limit mod z tending to 0. Z bar is cancelled with this number, therefore z bar del z plus z del z bar plus del z bar over del z. Now, or again simplifying this step, we get del z tending to 0, z bar plus z del z bar over del z plus del z bar. Now, as a function is continuous, now discuss this part. As del z tending to 0, del z bar also tends to 0. Therefore, this part is very small, it is negligible. Therefore, this term is written as f dash z equals to limit z bar plus z del z bar over del z. Del z tending to 0. And del z bar also tending to 0. So, this consider along real axis del z becomes this only, and del z bar also becomes del x cube, because along real axis change in y is 0. Del z is del x plus iota del y, but along real axis there is no change in y. Therefore, this term remains only this part and this remains only this part. Now substituting this value, we get f dash equals to limit del z tending to 0 z bar plus z as 1 by 1. This over this is 1. But along imaginary axis f dash z is limit del z tending to 0 is z bar plus z iota del y minus over iota del y. And this gives us limit del z tending to 0 equals to z bar minus z. When along real axis it is z bar plus z, but along imaginary axis it is z bar minus z, which is different. They are not same, they are not equal. Therefore, we can say that this function f z mod of z square is continuous but not differentiable at any point of the domain. But it is differentiable at origin. How it is possible? At origin, we know that at origin x and y are 0, 0. Therefore, z is also 0, z bar is also 0, z bar is 0, 0. So, at origin f dash z is 0 along real axis, and along imaginary axis also f dash z is 0. Therefore, function is both of the limits are equal, and hence we can say that function is a differentiable function. So it is a very important and an interesting example for this part to prove if function is continuous, if function is differentiable, then necessarily it is continuous. But converse part of the function, if function is continuous, then it is not necessarily differentiable. So first part is very easily proved, but for the second part we give an example, because this function is continuous being a real function, but it is not differentiable at any point of the domain or Argand plane except at origin. So this function is a particular case. It is differentiable only at the origin, not other than origin in the Argand plane. So the continuity is not a necessary condition to be a function or differentiable function. But here we conclude that The concept of the limit is a very important concept because we are finding the limit, and as in argument plane or as in a complex analysis, a point can move from a one point to other point by any path, not along a line segment joining those points, but from a point in this argument plane, from this point to this point. If this point is A and this point is B, then the point can move along any path, not necessarily from this line segment, along this line segment. It can move along this path also. This can move along this circular path also, or any other path. There are infinite many paths to join the A and B. If the limit exists and equal for all the paths, then only we can say the limit of the function exists. And for differentiability, we know that it is defined in a form of a limit. Therefore, it is necessary to find, but always, as we know, there is not need to find the limit. We know that whether function is continuous or not. Continuity must be must. If function is continuous, then we check differentiability. And most of the functions which is used practically in solving all the problems, for example, trigonometric function, exponential function, logarithmic function, algebraic functions, rational functions, by inspection we know that they are differentiable or not. So it is quite easy to find the differential coefficients of the function, and the rules to find the differential coefficient of a function or rules to differentiate the function fz are same as that in real analysis. For example, fz plus zz, differentiation of fz plus dz is f dash z plus minus gz dash if fz and gz are single valued continuous function defined in a domain D. Now the continuity is a necessary condition, therefore we put in as a definition of the function. The function if fz and gz are continuous function defined in a domain D and they are single valued function, then differentiation of their sum or difference is equal to the corresponding sum and difference of their differential coefficients. Similarly, differential coefficient of product of two functions is again first function into differentiation of second function plus second function into differentiation of first function. Of course, here variable is z, therefore we are differentiating with respect to z. Here only d means we are differentiating with respect to z. Similarly, the differentiation of quotient of the function, if this is the rule of the differentiation is the same, second function into differentiation of first minus first function into differentiation of second over the square of the denominator function. Yeah? So the rules are the same, and again function of function, if we differentiate f of gz, then it is equals to f dash gz plus into g dash z. For example, we know all these rules very well and use here at the same way as we are using in the earlier part. There are so many questions to find, but here we concentrate on the finding the limit in the reason if the limit along any path is equal, then only function is differentiable, otherwise it is not differentiable. This is the concept of the differentiability. Now we define analytic function in next lecture, and analyticity is a necessary condition for discuss the integrability of the function. Of course, here we are discussing only complex functions, and we have earlier defined complex functions. Complex functions differ from a real function because all the real variables lie on a line which we call real number line. But complex numbers and complex function both lie in a plane. Therefore, joining any 2 points of the on the real line is always a line segment, but in case of complex functions and complex variable, it is not always a line segment, it may be a curve. We take some more problems to discuss in these matters how they differ, limits differ from a line to a curve.